Let's take a look at a simple circuit where we basically have a power supply, some wires, and some kind of load that we're powering in the circuit. So I've got to open up our PhET simulation, and I've loaded in what I would call a simple circuit. You have your power supply. There's a battery. Everybody understands batteries supply some kind of power. In this case, it's charge supplied at a particular voltage, which we've discussed already. That charge can flow through conducting wires. These are called conductors. They're copper colored because they're typically made out of copper. And you have a switch in here which controls that flow. I can open it or close it. That's the on-off switch that is on appliances that helps control that flow. And you got your light bulb. That's the thing we're trying to power. Sometimes there's multiple things in that circuit, but right now we're focused on lighting this bulb. So I'm going to take a quick screen capture of this here. Take a quick snip. I'm going to throw it into OneNote, and let's start defining some of these terms and how they apply to what we're trying to do here in our class here. So this is, again, a picture of what I'm going to call a simple circuit. Now, if we were to do this class, in the actual classroom, I'd have you building this circuit. We'd put together all these elements. But right now, we're kind of limited to what we have at our disposal here with a PhET simulation. So right here, we have our battery. Right? This battery is also called our power supply. It is where we are getting not only the electrons electrons are there in the wire all the time, but really it's that push behind those electrons. It's where we're going to get that oomph, whatever's going to push the electrons through the circuit. Right? In this case, it's a battery. It could very well be your outlet, in your homes that are running those circuits, but this is our power supply. Typically, your power supply is going to have a positive end and a negative end. If you actually look at a battery, like this battery here, maybe a AA battery, you'll see that it's labeled as such. Right? And then up here we have what we call a switch. All right? A switch is a physical connector that has the ability to close by moving it, and that gives kind of like a bridge, like a drawbridge that allows for the completion of that circuit. So right now it's in the open position, and because it's open, there are no flow of electrons. All right? And when we close the switch, when the switch closes, that's when the electrons can flow. And we would say that we have a closed circuit. All right, let's continue on and look at our light bulb. So every circuit, we're trying to power something. If there's nothing to power, we would have what's called a short circuit, where the wire just goes right back to the source. We'll talk about what happens here. But in this case, we have a light bulb. And whatever we're trying to power, we call the load on the circuit. All right, so our light bulb is our load. All right, and so those charges are going to flow, and we're going to get this light bulb to light up. So let me go back to this simulation here, and I'm going to close the switch. And when I close the switch, you notice that this light bulb has lit up a little bit. All right, I'm going to open the switch again, and you see around this light bulb to the right, there are no little glowing lights here. But when I close it, the light comes on. And that's what happens in our normal circuit. And it's hard to see what's really happening. You don't see anything change except for the position of the switch and the light coming on and off. Right? And I think that's what's challenging about electricity. Right? We don't see what's actually happening in the wires because they're at an atomic level. So the nice thing is we can visualize what's happening here by having it show the current. So we'll talk about this concept. I'm going to have, here now we have electrons in this wire, and they're not moving anywhere. But the moment we close the switch, we get this movement of electrons. Right? That movement of electrons, you could think of it as a kinetic energy. Right? There's a friction, there's a heat that is released when you have friction, and that heat is going to show up in that thin little filament, that little wire, and that is going to produce light, right? It's going to emit light out of that hot filament, that hot tungsten wire that might be in that light bulb. Right? So this electron flow is something that we call current. Right? And so this current is a flow of electrons that is going to power our light bulb or our load. Right? And so right now, if you look at our light bulb, our battery, it makes sense, right? We have a positive end and we have a negative end. Those electrons really want to move back to positive, but there's this line in between. So if I go back to here, this battery, right, has this barrier that cannot be crossed by these electrons. And so those electrons want to really move to that positive side. And when we close the switch, they have the ability to move around. Right? And when they move, that's when we get that friction, that kinetic energy, and that flow of electrons in that circuit. So that's really what we're trying to do when we're running a circuit. Now, this view, drawing the pictures, drawing it visually of actually what we see is nice, but we typically see a different way to show a circuit, and we call this a circuit diagram. So it's kind of a shorthand way of drawing what we see above in kind of a simplified way. So our power supply, or our battery, we typically draw with a long line and a short line. That long line is typically the positive end and the short is the negative. So this is my power supply. So this is showing that we have a voltage, a potential difference at that point, right? And there's a gap there, which means those electrons can't jump across to that long line. So instead, we got to give it a pathway, right? And so my wires, I'm going to draw here, and I stopped right here. There's this junction, these nodes, and there's my switch that's open in this case. So this is my switch. And again, it's got the ability to close, right, which would allow that pathway to continue. These wires continue down, and I reach my load. Now, there's a couple different ways you can draw it. If you look at your simulation, the light bulb, if you switch over here, you can see this other mode. And you'll see the symbol for the light bulb on the left here. There's a couple different symbols. The one that I typically do is something that looks like this. It looks like a circle with a little zigzag in between it. And we'll talk about that shape as well. And then the wires continue and they go around, and we have a circuit. Right? So again, this is my load. In this case, this symbol most people would recognize as a light bulb. You have, again, the switch. We didn't define this above, but these copper connectors we call wires. All right, or even better, if you talk to an electrician, they would say they are our conductors. All right, they are typically made of metal. And in your home, that metal is usually copper. So you usually have copper wiring in your home, but aluminum would work, gold, if you have really fancy HDMI cables, you might have gold cables, but you're looking for conducting materials so that those electrons can flow really easily. Right? And so in that circuit, when I close that switch, right, I'm going to get a flow of electrons from the negative to the positive. So they're going to flow around through this circuit when the switch is closed and make this loop. And they're going to make their way to that positive end because that's where they're attracted to, right? They want to neutralize that charge. So this green line is the flow of the actual electrons in the circuit. All right, that's which way they're actually moving. They're going to move from the positive end where there are too many electrons, from the negative end where there are too many, to the positive end where they are missing in order to find that balance, right, to find that charge equilibrium. Now, the one thing that's a little confusing is before we really understood that it was electrons moving, people understood how electricity generally worked. And as we talked about with that convention with field strength, we typically deal with these positive test charge, which is kind of weird because it's really electrons moving. But we get this concept of a charge being a positive thing. And for that reason, electricians and in general working as with electrical elements, we actually think of current and the flow of electrons moving in this direction, which is actually opposite of what the electrons are doing, and we call this conventional current. Which isn't actually which way the electrons are going, but it's generally the direction that we assume that things are moving in the circuit. So it actually goes from positive to negative, and you can think of it as what a positive charge would do. It would be repelled from the positive end and go to the negative end. It's really not that important to really know the difference, but you might see elements of this being taught in different lessons if you look online. And if you look on here in our simulation, you can actually switch it to conventional current, and now you see it's flowing the other way, from the positive end to the negative end. In your home, the outlets will actually usually have one slot slightly bigger than the other, and it kind of looks like that longer slot for the positive end. And we call that the hot terminal. That's where the charge is coming from. That's the one that's powered. So actually, I think the electrons really come out of that end in your outlet, even though really they should come from the other. So it's a little confusing, but at the end of the day, what we're looking for is that closed circuit, that switch being closed. Right now, there's no flow, and now that it's closed, they have a chance to move. If I put the electrons in there, you see that the electrons can't move until you close it, and now they're moving along the flow of actual electrons. All right, so you get this movement of charge, and that's work that's being done. Forces are being applied to cause the electrons to move a distance. Right? So in that way, we actually have energy. Right? And so now we're able to power an appliance with this charge. Right? So I want to define a term here. I've mentioned it a couple times, but it's a new term that we've talked about. The first term that we already have talked about is this idea of voltage, right? The power supply is going to give us a voltage, right? A AA battery or a single A or a AAA or even a D battery is going to give us a voltage of 1.5 volts. That's a standard voltage for any of those batteries that you're going to put in like an RC car. Right? Voltage is the pressure. Without any pressure, electrons won't move, right? So that's what that power supply really does. It supplies electrons and some pressure behind them. But once they're moving, we now have what we call current. Current is the flow of charge. And by charge, I really just mean electrons, right? Because those are the things that can actually move. You're not really moving protons or the atoms. You're moving the electrons around because we have a conducting material, that copper, right? And if you think about current as like water, if you would describe current of a river or some kind of moving water source, you would really try to measure that as the amount of water molecules that pass by you over a period of time, right? If it's a really fast current, you would have a lot more water flowing past you in the same amount of time. And that's really how we think about current with electricity. It's the amount of charge that passes through a point in the wire over a period of time. It's a rate of charge flowing through the circuit, right? And so we can actually formulate an equation now. Current is equal to the amount of charge passing through over a period of time. Now, we actually have charge as Q. We've dealt with that. Time, we've already dealt with as T. Current is actually the letter I. It has to do with current intensity is where that I comes from. And so that's where I is. So you have to, what's tricky about this unit is we have these letters again that represent different quantities, and they don't always match up the word, right? Big C is actually coulombs, which is a unit for charge, which is using the letter Q, right? And so you can see the confusion that happens in this unit. But this gives us an equation for current, which is equal to the amount of charge over a period of time. And if you look at that equation, you can actually derive what the units must be, right? Well, charge is in coulombs, time is in seconds. You have coulombs per second is the unit for current, and that has its own name, which we call an ampere. And usually you see it shortened as an amp. So hopefully you guys have heard of amps when dealing with electrical circuits, AMP, and we use capital A for amps. And in our system here, we can actually measure current in this circuit. I'm going to switch back to the conventional view here, where you can see things move along. Right? We can measure that flow by putting in a device that measures current. Right? That device is called an ammeter. Meter to be measured, am as in amp. Right? An ammeter is a device that measures current. So if I have a circuit and I'm trying to figure out, well, how much flow am I getting here? What's my current? I can insert an ammeter into that circuit. Right? It's almost like you're sticking your finger in the water and feeling how fast the water is moving. Right? You don't really change the flow of the water. Right? So when you throw an ammeter into the circuit here, I'm going to throw this ammeter in. I'm going to break my circuit right here. I'm going to open the switch. I'm going to break this. And I'm going to throw an ammeter right in here. Right? I throw it right into the flow. So every charge has to pass through this ammeter. Right? Notice it labels current. And in doing so, this thing is kind of testing that flow. It's sticking the finger in the water. It's not changing the flow, but it will tell us how fast it's flowing. And when I close this, I see that this particular circuit has 0.3 amps. Right? And so I can measure exactly how much flow. There are 0.3 coulombs every second that this current is running. Right? That's what that means, 0.3 coulombs per second. Right? Now, one thing that's kind of interesting, we'll look at this in a lab, this battery right now has a voltage of 1.5 volts. Right? We've talked about voltage already. Right? Well, if I increase the voltage, think about voltage as being the pressure behind the charge. Well, what should happen to the current? Well, with more push or oomph, that current should move faster, right? And as I bump it up to 3 volts, look what happens to the current. It's now at 0.6. You see those electrons flowing faster. And some of you guys might have noticed that I can really get this thing flying around. And look at that flow. We really get that current to fly. Uh-oh. We're really stressing our battery right now. That battery would get really hot with this current flowing. There's so much friction flowing through it. So you can do some fun things here with our simulation and kind of get a sense of what happens when you get too much current going through a circuit. So this is a good little introduction to current flow, or charge flow rather, which we call current, and we'll be able to continue with some of these concepts here later.